Okay, so the first topic that we are going to talk about is something which works not only for the symmetric group Sn, it works for all groups. It's basically how to get representations or how representations across, let's say, subgroups. That's not really a very accurate heading, but the basic idea I'm talking about is this. We have already talked about this before. Suppose you have a group G and you have a subgroup H. So not a normal subgroup necessarily, just a subgroup. And if you know the representation for a group G, you can use it to immediately create a representation for the group H, right? That's very easy because having a representation for the group G essentially means, if you're talking about matrix representation, say, you have for all small g belonging to capital G, you have a matrix DG. And the map D from the group itself to the set of all matrices, n by n matrices, essentially works this way, that it's a homomorphism. dg1 g2 is dg1 times dg2. But of course, every member of capital H, so if small h belongs to capital H, then small h belongs to G as well. That's what subsets mean, and subgroups are of course subsets. And if you just take dH, they will give you a bunch of matrices which will definitely obey dH1, H2 is dH1 times dH2, because they are just inheriting that from the fact that they are these D's are actually representations of the original group, right? So if you have a representation of the original group, finding a representation of the subgroup is trivial. All you do is just pick those representation matrices which stand for those subgroup elements and drop the rest. However, what we are trying to do today is go the other way around. If you suppose know all the characters for irreducible representations for a subgroup, can you use them to figure out results about the group itself? Of course, you must realize that just doing just that is impossible. You cannot. A group has many more elements than a subgroup has, and a subgroup cannot possibly give you the entire information about the group. However, if you know the connection between the group and the subgroup, and in many cases you can use this and some other pieces of group theory to actually build up the character table for a big group from that of a subgroup. And I'm going to try to illustrate that today. Okay? Now, first of all, we have been saying this about any representation, right? This D could be any representation. I'm not making any claim about reducibility or irreducibility at this stage. But if, say, I have an irreducible representation of G. So we have D alpha, which is an irrep of G. Now, so if you restrict that irrep just to the subset H, subset provided by H, it gives us a representation of capital H. That's straightforward. The question is this an irrep of H? So what is your opinion about that? Is an irreducible representation of a group invariably an irreducible representation? Okay, of course, it's not a representation of the subgroup at all, but if you restrict it to the subgroup, you get a representation. Is this an irrep? Yes or no? What would you think?
It need not be an irrep.
Why?
Because in the subgroup you don't have some of the matrices, because like subgroup is smaller than a group, so you have lesser number of matrices, so there is a possibility to further block diagonalize it.
Exactly. So it may not be possible to block diagonalize all the elements of the group of DG rather. However, it may be possible to further block diagonalize if you just look at a subset, right? Because, for example, if you just picked one of the DGs, that would, of course, not be relevant here unless you're talking about the identity, because that would not give you a subgroup representation. But still, if you looked at only one of the DGs, you can always diagonalize it very often, right? Not even block diagonalize, completely diagonalize it. If you had to get, if you had to given say 3 or 4, you may be able to block diagonalize them all together. The same transformation may not be able to block diagonalize all the other matrices in the group. So it's very possible that something which is an irrep of G will induce a representation which is reducible in H. Look upon it in another way in terms of the linear operators behind the picture. Basically, when you say G is the representation for G is irreducible, what you mean is the linear operators involved, they form an irreducible set of operators. What that means is no subset of the vector space, no subspace of the vector space, or rather no non-trivial subspace of the vector space is invariant under the action of all of them. But now that you're taking only a few of them, not all of them, it's possible that there will be an invariant subspace for those few. They may not be invariant under the rest, but they can still be invariant under the ones we have taken. So a representation of G induces a representation in H, but an irrep of G may not induce an irrep in H. Of course, there are special cases. For example, 1D representations of G. They are obviously irreps because there are no smaller subspaces. You're already at one dimension. So if you restrict them to H, they will of course give you irreps, right? Because you can't go any further. You can't go any lower. But in general, an irrep of G will induce a reducible representation on H. Okay, fine. So that's one thing. And as we have been saying, there's a huge connection between classes on one hand and irreps on the other. So now let us look at the class connection. Classes in G. And what do they look like in H? Okay. So one very important thing is this. Suppose, okay, let me just list this out. Let's say we have G and you're breaking this up into many classes. Say C1, C2, and so on. Up to, of course, NC, where NC is the total number of classes of group G. Now, if two elements are conjugate, so classes, of course, means the connecting elements which are conjugate to each other. If two elements are conjugate in H, are they conjugate in G? That's a question to be asked, and vice versa. So, again, tell me, what do you think? Two elements. Of course, two elements, let's say, of course, if the two elements don't belong to capital H at all in the first place, if both of them don't belong to capital H, saying that they are conjugate in capital H makes no sense. So let's just pick two elements which are there in capital H. Of course, they are in capital G as well. So if two elements of capital H are conjugate in G, are they conjugate in H? That's the question. So what do you think about this? Remember, two elements are conjugate. Let's say H1, H2 are conjugate essentially means that there is some G in the group, so that H1 is G, H2 G inverse, right? So if they're conjugate in G, that means capital G has some element which does this conjugation for you, connects H1, H2 this way. Are they conjugate in H necessarily? Yes or no? Yes?
Need not be because the G might not be in H.
Right, exactly. So this capital G has more elements than capital H. So it's possible that one of those elements which did not belong to capital H conjugated H1 and H2 to each other. That is, the conjugacy class relationship that we had, that H1 and H2 belongs to the same class, is correct in capital G but may not be correct in capital H. Having said that, what about the converse question? If two elements are conjugate in capital H, are they conjugate in capital G? So basically you have two elements, H1 and H2, and there is an element in capital H, let's say small h, that this works.
They should be.
Of course, since small h is an element of capital H, it's also an element of capital G, right? So this, of course, is exactly what you want for conjugation. So basically what you have is elements which are conjugate in capital H are definitely conjugate in capital G, but not necessarily the other way around. Okay. So what does that tell you about the relationship between the conjugacy classes of capital G and conjugacy classes of capital H? Of course, it might so happen that there are conjugacy classes in capital G which have no elements in common with H. Okay, right? That's very possible. But there are entire conjugacy classes in capital G which do not have any elements in capital H. Okay, so the question of them containing any conjugacy classes or not, or the conjugacy class structure of capital H involving such classes, is really not relevant because they don't have any such elements. However, suppose C1 has at least one element in capital H, that is C1 intersection capital H is not null. If that happens, what can you tell about the conjugacy class structure of capital H? Say I'm going to denote classes of capital H by, let's say, capital K. I'm just using different notation just to distinguish between these two. So C1, what can you say about C1 and the relationship between the classes of H? Say, first of all,
Either
yeah.
C1 is the same, like H has the same class as C1, or C1 breaks up into distinct classes.
Okay, C1 breaks up into distinct classes. That's correct. Okay, let's put it this way. In general, C1 may be a single class in H. It's possible. But in general, what's more possible is you may have situations like this. C1 breaks up into K11, K12, and so on, which are classes in H, and let's say ultimately K1 in 1. Okay. But this will be entire complete classes of H. Complete classes of H will fit inside classes of G. There will not be a situation like this, that a part of a class in H is in C1, another part is in C2. That can't happen because every conjugacy class in H, every element of conjugacy class in H is already conjugate in G, right? So, okay, let me just, this is an important point, so let me just stress that. So what we are talking about is a situation where you have two classes G and H, two groups G and H. H is a subgroup. G breaks up into conjugacy classes like this. And from this point on, all conjugacy classes are disjoint from H. I've just labeled them this way. But each of the classes which are not disjoint from H, they will split up into several conjugacy classes. Now, the notation for this discussion is going to be a bit messy, so I'm just going to pick one which I'm not very happy with the notation, but basically this is the best I can do, I guess. So each CI, either CI intersection H is null, in which case that means I belongs to one of these classes down here, which do not have any overlap at all, or Ci is a union from I equal to 1 to Ni. Of course, the number of classes of capital H which fit into each class of G, that depends on which class you're talking about. So 1 to Ni of Ki, comma, okay, that's a bad notation. Can't be I. This has to be J going from 1 to Ni, Kij. Is this notation clear to everybody? That
Yes,
is,
sir. So,
yeah.
is there a possibility that some of the elements of Ci are in H and some of them are not in H?
Okay, that's a good question. So is it possible that some elements of Ci are in H and some other elements in the same class are not in H? Yeah, that's right actually. In fact, uh, what I said here right now is wrong. Ci is not a union of this. Okay? You are perfectly right. It's very possible that some elements might be inside and some elements may not be inside. So, at all in it. So this is correct, completely correct. Actually, what I really should say is a statement like this. Ci is not a union of classes in H. You're perfectly correct. But Ci intersection H, those elements in Ci which are common with H, those would be a union of complete classes in H. Is this okay with everybody?
Yes, sir.
And this is what is going to be critical. In fact, this issue is critical. Whether there are elements in Ci, there would be elements in some class which are not in H at all, but some of the others are. This statement that I am making is either Ci intersection H is null, in which case there are no common elements. But if there are common elements, then the common elements break up into classes. Not all elements of a class Ci breaks up into classes of H. Okay. So this is a basic. Okay, there's nothing about the permutation group here. This is a general statement about all groups and subgroups. Number one. Number two is, so far we have not talked much about representation, except for the fact that irreducible representations of a group may give you it may induce a reducible representation of subgroup. So now let's connect the two issues together. Let's say I have an irrep labeled alpha, d alpha of capital G. So small g belongs to capital G. Then, of course, this itself will not give you a representation of capital H because small g may not belong to capital H. But in particular, let's talk about an element small h right now, which belongs to capital H as well. So d alpha H, what will this be? This will be, okay, I should not really write equal to here, but in principle, I can always block diagonalize this. So if I block diagonalize this, I will always be able to break this up into irreps of capital H. So I'm using the notation capital D for irreps of capital G, capital delta for irreps of small h, of capital H, sorry. And the breakup may be something like this. Right? I hope everybody understands what I mean. I mean that once I pick up all the d alpha h's for the subgroup, I can block diagonalize them all together into a form in which each irrep of capital H is going to come m alpha mu. The muth irrep is going to come m alpha mu times, where m alpha mu are of course non-negative integers. Is that okay with everybody? Any reducible representation can be written down. This node is an irrep only for capital G. For capital H, this in general is reducible, and any reducible representation can be written down this way. Okay? Yes or no?
Yes, sir.
Okay, then let's talk about characters. Chi alpha corresponding to the element H. Of course, here I am using the same sign because the matrix may not be block diagonal, but it can be block diagonalized. But characters, of course, are independent of this process of doing a similarity transformation. So for characters, you really have an equality.
Is this summation a direct sum?
Yeah, this is a direct sum at the matrix level. That is, you can always write this matrix as a direct sum of block diagonal pieces. But you can also write this as summation if you just use the convention that in a direct sum, this block is there, every other element is 0. Then you can also think in terms of an actual matrix summation. But this is a symbolic representation. All you say is you can block diagonalize this to a form which has blocks. This one is an actual sum. But here I'm going to use characters in capital H, and I should use a different name. So let me say I'm using this notation. Phi. So chi's are characters of G, of the irreps of G, and these are characters for capital H. Okay? Two different groups, so they have different character tables. So I'm just going to use different symbols for that, just to avoid confusion. Okay? So this is the general situation. Now, how does that help us to note that what we are saying is capital H is a simple group, and because it's a simple, or it's a smaller group, and because it's a smaller group, it's typically easier to find out its character table. So I'm assuming I know the character table for capital H. Can I use it and some extra information about the relationship between the two groups to find out a character table, or find out the character table for capital G? That's the question. So this is a relationship that we know exists. Of course, at this stage, we don't know what these integers are. All we know that there should be some non-negative integer sitting here. So just knowing the character tables will not help. Okay, and in any case, this just gives me the characters for those elements which are in capital H. This by itself does not tell me anything about those elements which are not in capital H, right? So while this looks like a perfectly good relationship, by itself, it seems very surprising that this can at all tell you anything about chi alphas for the entire group capital G. Is that okay? What we are going to do is we are going to show that that's really not true. That is, you can actually exploit the group structure and really find out quite a lot from this. So let me just write down this. Or there's a relation up here. Okay. So of course we all know that Kaiser's actually class functions. So instead of focusing on H, let's say Ci intersection H is not null. So you're talking about a particular class of capital G which has some elements in capital H. For such a class, you can always write this, right? Okay, what is going to be the argument here? Which class is going to sit here?
Kij.
Okay, but with J? I can understand. With J?
Summation over all J's.
Just hold on. I'm getting a call. I'll just. Hello. আমি একটু পরে তোমায় ফোন করি তাহলে ক্লাস হচ্ছে ঠিক আছে ওকে So which J? There are many J's, right? J could run from 1 to, well, how many J's? That depends on how many classes are there inside Ci. So how many classes of capital H are there in Ji? Say 1 to Ni. So which J are we talking about here?
Summation over all J's.
Really? Why summation? Okay. Anybody else has a different idea first? So notice that what we started with was character of an element, right? Chi alpha for H. This H is an element of capital H. It's also an element of capital G. Let's say it belongs to the class Ci. Okay. That is what tells me what the character for the class Ci is going to be. Because remember, character being a class function, you can pick out any element from the character and find out its character. That will be the character for the whole class. Now this small h, will it belong to all the kij's or only one of the kij's? Yes? That's a sort of trivial question to ask, but what is it? Will it belong to all of them or will it belong to only one of them?
It belong to one of them.
Of course, it has to belong to one of them. It can't belong to all of them, right? Because these are classes, right? These classes are classes in capital H are classes as well, right? So they are partitions. They don't have common elements. So small h has to belong to only one of the kij's. So strictly speaking, this relationship should only work for that particular j, such that kij contains small h. Okay. But having said that, I could have taken any one of the small h's which belong to Ci intersection H, right? And if you run over the entire Ci intersection H, this H will belong to Kij for any one of the J's, right? A given H will belong to only one Kij. But as you go over the entire class Ci, of course, there will be some elements which don't belong to capital H at all. We are not talking about them. But the elements which do belong to capital H, they will run over all of, some of them will be in Ki1, some of them will be in Ki2, some of them will be in Ki3, and so on. Is that okay? So let me ask you one second. What does this relationship work for? Will it work for only one of the J's? Will it work for the sum, or will it work for each of the J's separately?
It will work for each of the J's separately.
Right. It will work for each of the J's separately. Now that's quite surprising. Remember, the left-hand side, of course, is independent of the J. The right-hand side could very well depend on J because the characters for different classes. Remember, Kij's are different classes as far as capital H is concerned. So the phi's have no obligation of being equal to each other. Whereas on the left-hand side, all of the small h's you have picked belong to the same class of capital G, so they must have the same character. On the right-hand side, you have elements which belong to different classes in capital H, right? They don't have an obligation of having the same character at all. So, but no matter what Kij is, for each and every one of the Kij's, the same relationship must hold. And that actually is quite a severe restriction, and that in a way is responsible for the next result we are going to talk about. Okay? But this is important. This is a class relationship where K alpha Ci, as long as Ci has an element which is in common with capital H, K alpha Ci can always be written down like this, where M alpha mu's are some non-negative integers. Some of them, of course, could be 0. And you have the characters for the classes which are inside Ci of H. And doesn't matter which of the classes you use, you always get the same integer combination to give you this. Is that okay? Now, having said that, let's now look at a particular class Cj such that Cj intersection H. Okay, I actually should have written like this. Let's look at a class Cj which has no intersection with H. So if I take chi alpha Ci, which is the expression on the left here, multiply it with by chi alpha, same irrep of capital G for Cj, conjugated, and sum over all alpha. What am I going to get? Any answers? Remember, I is the specific class that we are talking about, some class which has some element in common with capital H. And now I'm taking a different class, has to be a different class because this is disjoint from capital H. And I'm forming this combination. Can you tell me how much this is going to be? Okay, let me just give you a quick reminder of basic character orthogonalization theory. Two results that come in. One is NCI, number of elements in the ith class, chi alpha Ci, chi beta Ci star. The sum goes from all I from 1 to curly NC, so over the entire classes. This is delta alpha beta, right? Times mod G. That's the orthogonality theorem, orthogonality of the class vectors. But in addition to that, you have another result, which is if you take. So this is a sum for over all the classes and not necessarily the same irrep. On the other hand, if you took this chi alpha Ci, exactly what I have written here, chi alpha Cj star and summed up over all irreps, what will this be?
Delta ij.
Well, almost, except that the vectors which are there's a normalization to worry about, right? This will
Mod
give
G
you
by NC.
mod G by which NCI. Of course, doesn't matter whether it's NCI or NCJ because it's zero anyway when I is not equal to j. Okay, so this one is the orthogonality relationship. This one up here, and this one is the completeness relation. That all the characters form a complete, all the character vectors form a complete set. Okay, so both of them are very important in our applications, and in this case, because there is sum over all irreps, this is definitely going to give you this result. But how much is this? In our specific case, these two results are general statements for all groups. For our specific situation, how much is this going to be? Come on, it's going to be mod G by the number of elements in the class Ci times delta Ij. But what will delta Ij be? That's the only thing you have to worry about.
0.
Has to be 0. I hope everybody gets that. These two classes are definitely distinct, right? One of them has an overlap with H, the other one does not. So they are different classes, period. So because they're different classes, the completeness relationship will definitely give you a 0. But why is that important for us? What's important is, if you look at what chi alpha Ci is, then you get this sum over all irreps. This is the sum over all irreps of in capital H, of capital H, m alpha mu phi mu Kij. Then you have chi alpha Cj. Okay, there's a bad notation, right? I should not use J here. Maybe I will say chi alpha A. You understand why this is a bad notation, right? I don't want to confuse with this J, which I multiplied from this J, Cj star, summed over all alpha. This is going to be 0. Right? That's just this sum rewritten, nothing else. But now let me just change the order a bit. The sum over all irreps in capital H. That is done later. First you do this sum over alpha, all irreps of capital G, of m alpha mu chi alpha Cj star phi mu Aia. Okay, this is going to be 0. Now, what does that tell me about this? On the face of it, all it's telling you is that that some linear combination of the phi mu ki is 0. Okay. And what are these
The
phi mu ki
brackets
is by
could
the way? Sorry.
characters
Yeah.
of the bracket could be characters of some other irrep, like not mu irrep. some other class, KIH or something.
Well, could be because of you're thinking in terms of orthogonality, right? True,
Yes,
but
sir.
which ki is this? Which I and which a are this valid for? First of all, which a is this valid for?
All is.
All a's. Now, which i's? This is
All
valid
is
for,
with intersection with H.
yeah, all i's with intersection in H, which means this is valid really for all the classes in capital H, right?
Yes.
So if this is going to, so what does, so now would you care to modify your statement? This thing is valid not for a specific class KIA. If that had been the case, then this could be some non-trivial number. But this works for all the classes which are there in capital H, right? Because what we
So
have picked, yeah, so what can you say about this bracket?
should be 0.
The only thing that this bracket can be is 0. In fact, you can, of course, do this formally by then using the orthogonality of the characters in K of H. You can write this down formally, but it's pretty easy to see that the only possibility is going to be that this is going to be 0, and so its conjugate also is going to be 0. Of course, if you take the conjugate, the star goes away. These are integers, so they are real anyway. So this particular combination has to be 0. Okay. So that's one relationship that we have already got. If you have a class in capital G, which is not, which doesn't have an overlap with capital H, then this particular combination has to vanish for that. Now you might say that's really not telling much because we don't really know what M alpha mu's are, right? But we know some combination of the characters for all irreps, for a character of a given Cj, but for all irreps, it's going to vanish. So some information we have got. What is way more important is actually what happens when there is an intersection. Okay. So now, in fact, this is one result. Okay, this is also important. The other part of the important result is figuring out what happens for those classes which do have an overlap. So let's go back to that. And of course, what happens when you have an overlap is this. Chi alpha Ci has to be some combination here. So let me just try copying this and writing it out again. Or maybe I will just write it out again. Copying is too much of a bother with this. Now let us carry out a sequence of steps, some of which will look a bit sort of like magic for the time being, or at least will look sort of unmotivated to begin with, but you will soon see that they are not really unmotivated. So what we'll do first is we'll do this. We'll start with the left-hand side. Notice that mu is already summed over, so you can't really do anything further with mu. But you can always do this. You can take some new, some other irrep label. Again, irreps for capital H, remember. With the same KIA, take the conjugate of that. And not stop there. Multiply this by the number of elements in KIA and sum over all IA. Of course, when I say sum over all IA, I mean sum over all A from 1 to Ni, the number of classes which are there inside Ci, and then sum over all I. But if I do that, but what I'm really doing is I'm summing up over all classes of capital H. Everybody agrees with that? Remember, the classes in capital H can be broken up into a bunch of classes which are there in C1, in another bunch of classes which are there in C2, another bunch of classes there which are there in C3, and so on. But if you take all of them together, you've got all the classes of capital H. So if I do this sum, of course I can't do this sum only on the right hand side, I have to do it on the left as well. So it's number of elements in this particular class times phi nu okay. But can anybody now tell me why I did this? What happens to the right hand side here? If I do this, remember the right hand side originally had a sum over mu, and now I have a sum over all classes of capital H. And these are finite sums, so you can always switch them around. What happens if you do the sum over capital H first, over the classes of capital H first? That is, this sum first. What happens to this? Okay, when I'm looking at a sum over I and A, which terms get summed? This one doesn't. This is a constant as far as that sum is concerned. This, this
orthogonality
this.
theorem in H.
Yeah, so we have just written down every term you need to just use the orthogonality for characters in capital H, which means that this is going to simply be number of elements in H times delta mu nu. Is that okay? Which of course simply means m alpha nu, there is a sum over mu, remember, times mod H. Is this clear to everybody?
Yes, sir.
Okay, fine. So that's one step gone. This is a rather lengthy derivation, so there will be more steps to come, but not many more. We are near the end now. So what we have is m alpha. Okay, let's stick to mu mod H, but that's going to be sum over all classes of capital H pi mu. Of course, this nu is just some phi index which I can relabel as long as I'm doing it consistently. KIA star. So that's what we have. So this summation on this side is sum over all classes of capital H. Now what we are going to do is we are going to use orthogonality again, or rather not orthogonality really, because I'm going to use it now for the capital group capital G. But in capital G, okay, what do you have on the right hand side? You have the characters chi alpha ci. Okay, right? So if I multiply this, so I'm going to now just use completeness of the character vectors in capital G. So I've already used orthogonality in capital H. Now I'm going to use completeness in capital G. And for that, all I'm going to do is take whatever is written already this is already what you had, but in order to impose completeness, note that here the alpha is not summed over, I is summed over. The reason why I can't use orthogonality in capital G, this is something which is important to understand. It's not arbitrary that I'm using orthogonality in capital H and completeness in capital G. In capital H, when you use this orthogonality here, what you exploited was the fact that sum was over all irreps. So mu was a dummy index. You couldn't sum up over. You couldn't say let's multiply by mu and do some extra summation and then, because for then of course m alpha mu will always come in for the right, and m alpha mu's are well, things you don't even know or have no control over right now. Okay, which is why you avoided mu. You brought in a new irrep phi nu, some other label, but kept the same KIA and summed over to get orthogonality. Here, on the other hand, the class index I is already summed over. So you cannot really, and this is, of course, this is weighted with extra factors nKIA and phi mu KIA and so on. These all depend on I. You can't just say, let's do another sum over I by bringing in chi beta, C, say Ci star. But what you can always do, because this alpha is a free index, always do this chi alpha Cj sum j, and we are doing a sum of the, we are multiplying this and we are doing an overall sum over all alpha. Is this okay? You can do this, right? On this side you have m alpha mu mod h, Cj, sorry, Cj star. You all agree that we can do this? And now that if you all agree, then you should be able to tell me what you get when you do this.
The left hand side should be 0.
Left hand side is 0. Why do you say so? Because we showed it to be 0 a while ago, right?
Yes, sir.
No, we showed it to be 0 when J was one of the classes which did not have an overlap with H. But here I'm not using that notation any longer. This J is any class. Okay. So the left hand side is 0, it will not work. Not that, in fact, I am interested in the left hand side really. It's going to be 0 when J is a class which does not have an overlap with capital H. We have already established that. But right now we are allowing J to run over the entire set of classes of capital G. Okay, so the left hand side will not in general be 0. Focus on the right hand side. We have done a sum, right? We had a sum over all classes of capital H. And now we have a sum over all irreps of capital G. But this sum, by the way, we can of course interchange these sums because they are finite sums, no problems. But if you look at the sum over alpha, which terms participate in that? This one participates in that, and this one participates in that, right? The rest are independent of alpha. They will sit outside that sum. So if you do a sum over alpha first, what do you get?
Mod J by NCI delta IJ.
Delta Ij, exactly. Of course, this actually bears out what you said a while ago. You said it would be 0, but of course, if Cj has no common elements with capital H, then remember this sum runs over all classes of capital H, right? This is a sum over all classes of capital H. So when you're doing this sum runs over all the classes of capital H, but if capital G, this Cj was completely disjoint from that, then of course it will not be, it will never get delta Ij to be non-zero, you will always get delta Ij to be 0 for every term, so the right hand side will vanish. But in general, the right hand side will not vanish. If we're talking about an arbitrary class of capital G, what will the right hand side be? It's actually pretty simple now. There's some running over J and you have a I and you have a delta Ij here. So what will you get? Mod G, of course, will come out. What else?
NCJ, NKIJA, 5 new KIJ.
No, this is where you have to be careful. Note that this was a sum over all A running from 1 to Ni, then a sum over I. But in this entire sum, only a few terms will give you non-zero values, but not necessarily one term. That is, all the J's which do have over. So basically, which terms will give you non-zero values? Here. Any class which is inside Cj will give you a non-zero value because that will be one of the KJ's. So this really will be what you will get. Sorry, not J equal to, that's wrong. This index A okay. Does this make sense? That is, when you sum over all the classes in capital H, most of them will give you 0 because of the delta ij's here. Which ones will give you non-zero values? Only for those classes in capital H which are actually in the class Cj. They will give you non-zero values. And so this sum which was over all classes essentially becomes just a sum over those classes in capital H which are in Cj. All the others will give you 0. And just to sort of make this look a bit better, let me just do one thing. Let me get rid of this middle line and yes, I should. And what I will do is I will just move them closer to each other. So this is what you end up with. Just think about it a bit. It's really just, if you find this very difficult to think about, take a look at the concrete class, concrete group, take a look at its examples and figure out that this is exactly what it's going to be. But now that you have this, what does it tell you about, sorry. Look at the left hand side. The mod h, of course, is a constant, so it can move out of the sum. And on this side, what do you have? In fact, you can divide. Is this okay? All I've done is move the mod h from the left to the right. And of course, conjugated the whole expression to get rid of the stars. Mod g, mod h, these are just integers, so conjugation will not affect them. Is this okay with everybody?
Yes, sir.
So this is, of course, a question like that makes sense in the negative order. That is, if it's not okay, you should actually tell me it's not okay. But this is Frobenius's formula for compound characters. The same Frobenius whose name you have read a lot in differential equations. The same fellow. In fact, he did a lot of work in group representation theory. In fact, most of his work is in group representation theory. And what does it really say? It says something like this. Take a look at this quantity m alpha mu chi alpha Cj. I've already seen earlier, that is 0 if Cj does not have an intersection with H. And if it does have an intersection with H, what we have got is this. Just take a sum over those classes in H which are contained within Cj. You don't have to worry about other classes, only those classes. Multiply by this quantity, which are numbers which you get even without any reference to representation theory. Order of the group G, order of the group H, how many elements are there in classes? Okay, this is Kja, of course. And multiply by these characters for the class Kja, which were characters in the group capital H. So what's so great about this, if you might ask? But we still don't know the M alpha mu's, right? But can anybody suggest what's so great about this? Why is this a useful result to have? The left-hand side which you have here, what kind of an object is this? M alpha now you have M alpha mu chi alpha Cj for all classes, right? Whether the classes have overlaps with capital H or not. All classes of capital G featured in this equation. So every class in capital G, you have this relationship. The sum over M alpha mu chi alpha is a known quantity. Something you can figure out if you know the characters of capital H.
We can get a simultaneous equation on M alphas.
Oh, unfortunately, you can't because you don't know the chi alpha C's, right?
We know the bigger representation of the bigger group.
No, we don't know the representation of the bigger group. If you knew that, then all this would be trivial. You wouldn't have to do anything, right? Our assumption is you know the representation of capital H. That is, you know all the phi mu's. Okay. So right hand side of this expression, you can calculate directly because zero, of course, there's nothing to calculate. And here, only quantities which you have are just about the group structure, number of elements, and so on. In fact, you can think of this NCG by mod G. You can rewrite this as NKJA by mod H. Fraction of elements of the capital H which are contained in this particular class divided by NCG by mod G. Cj by mod G, right? So this is sort of a ratio between fractions of elements which belong to a particular class. That's something which depends only on the basic structure of the group, not on representation. I'm assuming I know the character table for the subgroup. Remember, the whole aim here is from the subgroup, can we figure out things about the group? What we have here on the left hand side is a quantity which does involve characters of the bigger group, but it would be useless apparently because you don't know the characters of the bigger group yet. Those are the things you're trying to find out. Yes, quickly. This should be pretty easy.
Sir, if you don't know chi alpha CJs, we did write mu alpha in terms of chi alpha CJ. So that means we can't really calculate mu alphas.
Right, you can't. So why would we still insist that this is a breakthrough? I'm saying that this is a important result which you can use to find out chi alpha CJs. Any idea how? let me remind you that this is not all you know. You know a lot about characters, which you have already used to build up character tables. You know, for example, that characters are orthogonal, right? You may not know what the characters are, but you know that they will be the orthogonal relationship. Okay, you also know how to the irreducibility criterion. Given a bunch of characters, even without the character table, you can find out whether this is reducible or not. In fact, you can even find out how many irreps are there. Right? Now, what you have here, and what is important is M alpha mu's. What do you know about M alpha mu's? Nothing much, except that they are non-negative integers, right? Is that okay? That's all you know. But if you took some irreps and took the characters and multiplied by a bunch of integers, one for each different irrep, and summed over, what will you get? You will get a character for a reducible representation, right? It's a valid character. Remember, you can't. One thing which we have emphasized before. You can't just take a bunch of numbers, one for every character class, and claim that as a character, right? Because there are some very stringent relationships which the characters must obey. But here we have actually found a character of some representation. If you knew the chi alpha g's and then took some some non-negative integer combinations, you would definitely get a character for some representation. Is that okay? Is this okay? This is a non-trivial statement I'm making. All I'm saying is, if you know the irreps, okay, I'm now going back with the premise that suppose I know all the irreps. Okay, I know it's a full character table for the group capital G. Then I can take some line of that irrep, some of the lines, and multiply them by some integers and combine them together. I get the character for some representation. Is this true or false?
Sir, could you repeat the statement again?
All I've done is something like this: taken some characters from the character table. I'm doing this for every group element. Of course, I'm taking, this is not just statement about only one G. This is true for all G. I'm doing this. I'm taking the characters for G, multiply them by some non-negative integers, adding them together. Is this the character for a representation of capital G?
Character for a reducible representation.
It's a character for a reducible representation, of course. It's a character for a reducible representation in which the alpha irrep occurs in alpha times. Okay? Right? But it's a valid character. Let me point out that an arbitrary bunch of numbers thrown in, one for every class, does not give you a valid character. This does give you a valid character. Okay? Right? Now tell me, what can you say about this? This quantity. I don't know what the M alpha mu's are, but I know that they are non-negative integers, right? Is that okay? So what does that tell you? It tells you that the left-hand side of this expression is the character for some reducible representation of capital G. Is this correct? Yes or no? If it's
Yes.
not
Yes,
yeah.
sir. Should
Because M alpha mu's, I don't know what they are. They are some non-negative, but I know that they are some non-negative integers, right? Because they are the number of times the muth irrep of capital H occurred in the alpha irrep of capital G, right? So they are non-negative integers. We are sure of that. So what we have on the left-hand side is we have sort of, notice what we have done. We have sort of switched the M alpha mu's from multiplying the delta mu's into multiplying the chi alphas. So we have sort of had a role reversal here. I'll just use the orthogonality and completeness relations to switch the role. But once you have done that, this quantity on the left is definitely the character for some reducible representation. And okay, a bit of terminology which we have not perhaps introduced so far. You call a character simple when it's the character of a irreducible representation. So all the character lines that we wrote down in the character table, they were simple characters, and this is called a compound character. In general, a compound character is a character for a reducible representation. And what we have found out is that every subgroup, once you have a subgroup, the subgroup will tell you something, will be able to tell you some compound character of your group. Not the character for an irrep, but some compound character. Okay, that sounds like not much, but you will soon see that it's really very useful information. Okay, one more thing. And there's one compound character which for every group which is almost trivial to find out from here. Of course, on the right hand side, when you are doing the calculation, what you are putting in, what? You're putting in the characters for the irreps of capital H, right? So that will of course vary from capital H to capital H. Even for the same group G, you would have several subgroups, and for each one of them you can get to use this. But no matter what capital H is, there's one representation which every capital H has. What is that? One representation which every group has.
Trivial representation.
The trivial representation, and that's an irrep, right? The 1D representation there is an irrep, right? So, and that of course, remember, is the character is 1, no matter which class you belong to. So then what you can do is you can immediately write down one compound character for any group from the subgroup thing. One obvious compound character for any group G is given by choosing this, say M alpha. That, of course, the trivial one is always written 0. So M alpha chi alpha 0. Chi alpha C, okay, Cj. Could of course say replace this by I here, is given by what? Given by this side. What is that? Is mod G by mod H, number of elements in the class Cj, that goes below. But you have to be a bit careful. What goes in the numerator here?
NKJA NJ.
NKJA times NJ, you mean? Times.
Yes.
This is 1. Well, not really. The NKJs may be different subclasses. You get to multiply by a number when every contribution in the sum is the same. Right? Here, NKJs is the number of elements in the eighth class of capital H, which Cj breaks up into. Right? So when you add them all together, you can't get to multiply by the number of such classes, because each class is not equal in length necessarily. But what you do get is something pretty simple. Not NKJ NJ. You can just rewrite it by
NCJ.
Oh, of course, that would have been a bit bad because that would have entirely cancelled this. Let's use the notation NKJ, not NCJ. You told me yourself a while ago that not every element in CJ may be in H, right? So what do you really get? You get the sum of all the class sizes which are in CJ. And when I say class, I mean classes of H. Sum of sizes of all the classes of H which are in CJ, which simply means how many elements of CJ are in H. Okay. And this formula works for both so this formula works irrespective of whether there's an overlap or not, because if there's no overlap, then NKJ will be 0, so you do get 0. Right? So you see, one compound character is very easy to write down. All you do is take a class. So what does this formula tell you? A character for, you're writing down a character for some reducible representation for the group G. All you have to do is look at the class Cj, okay, and form this number mod G by mod H, which of course is some integer. Remember Lagrange's theorem. And you multiply that by, well, the fraction of elements of Cj which are in capital H. Right? If all of Cj is in capital H, then that's 1. If only a part is, then you just put in what part. That's it. And that gives you a compound character. Pretty simple formula to remember, right? Is that okay? Yes, no, maybe.
Sort of, sir.
Okay, let me just give you an illustration now by an actual action. Okay, so now what we will do is, okay, this particular result that we have, this is our critical result. Even now that the result depends on the number of elements in the class, I can actually even drop this line, because this line essentially is telling me is 0, but if there are no elements in the class, if there is no intersection, then there are no elements of the class. So this formula essentially covers every base. So how do you use it here? So let me just show you this in usage, and then you will see what this formula really can help you to do. So for this, what we will do is we will just illustrate this by trying to build up character tables for the essence for the small n's. This same formula was actually used by Frobenius to develop the theory of the representations for all Sn, in fact for an arbitrary Sn, and he had a very nice combinatoric picture which came out of this formula, which essentially is what Young tableaus actually tell you. But today, just to illustrate this result, what I'm going to do is I'm going to keep life a bit simple. I will just start with small classes, not use the most general formula which involves a bit of combinatorics. We will talk about that later, but I'll not talk everything about that. I will just give you the hints about that, and somebody may fill in the gaps there as a topic for the lecture. But for the timing, let me just illustrate how you could use it possibly for small n's. So let's start with S1, number of permutations of one object. How many elements are there in S1?
One element.
One element, and of course we are going to talk of classes to label, and S1, and remember for permutation groups, classes are in one-to-one correspondence with the cycle structure. So there's only one element here and there's only one class, nothing we have to talk about. So I'm not going to use our theory for S1 or S2, but I'm going to show you how it translates to S3. Okay, what are the conjugacy classes? 1 square simply means 1, 1. That means a cycle structure where there are two 1 cycles, which of course means of the 2 elements, 1 is a cycle of its own, 2 is in a cycle of its own. So what do we call this element normally? This permutation, what do you call it? I hope all of you remember this notation. This is the cycle notation for the permutation. What does it tell you? It tells you 1 stays 1, 2 stays 2. So which permutation are we talking about?
Identity?
This is the identity permutation, right? There is nothing. 1 stays 1, 2 stays 2. On the other hand, the other cycle structure is 2. You have to be careful about this notation. This is the cycle structure. 1 square simply tells you there are 2 1 cycles. And this says there's a 2 cycle, which means the 2 cycle is 1, 2, which is of course transposition. 1 goes to 2, 2 goes to 1. Right? So these are the two In fact, for S2, there are only 2 elements and each of them are sitting in a class of its own. The numbers which I'm putting up here are nothing but the elements, number of elements in a class. They're both 1. And I already know 2 representations for this. 2 correct. So the trivial one, everything gets 1. And there's a non-trivial one which I can even write down from basic theory, which is this. Remember, the standard theory, which is trivial for the theory, from the theory of representations, is if you have an even permutation, you apply 1. If you have an odd permutation, you give -1. That's a so-called alternating representation which every SN has, right? You're clear that that's a representation, right? Remember, for 1D representations, characters are basically the same as the representation matrices. So what does this stand for? In quantum mechanics, this would stand for the fermionic thing, right? If you interchange, you get a minus sign. But all we are really saying is standard representation of permutation of 2 objects. One would be the case where even permutations count as 1, odd permutations count as -1. And because odd times odd is odd and even times even is even times odd is odd, and so on, it's very easy to see that this will give you a representation every time for every SN. So S3, those were rather trivial, no calculations involved. For S3 also, this is 3 1 cycles, 1 stage 1, 2 stage 2, 3 stage 3. This is the identity. Then you have 1 2 cycle, 1 1 cycle, right? And then the third possibility is a 3 cycle. Okay. Yeah, these are the only 3 possibilities, right? 3 can be either 1 plus 1 plus 1, which is the 1 cube thing, or it can be 2 plus 1, 1 2 cycle, 1 1 cycle, just 1 3 cycle, right? Is that okay to everybody? All possible cycles are counted.
Yes, sir.
Now, how many elements to each class? This one is absolutely trivial, but in general, if you have 1 to the alpha, 2 to the beta, 3 to the gamma, this kind of cycle structure, that is alpha 1 cycles, beta 2 cycles, gamma 3 cycles, and so on, we had already figured out a general formula for the number of elements in the class, which is, if you took all these numbers and wrote them down, okay, and these brackets indicate which cycles you have, okay, then there are n factorial ways of permuting all the numbers together, but then you have to realize that not all of them give you different permutations, because, for example, if you had, say, 3 1 cycles with 1 2 3 in them, and then you have 4 5 6 7 8 9, maybe 3 2 cycles, then 10 11 12 1 3 cycle, maybe another 4 cycle, let's say. I'm just writing them zigzag so that you can see that they're distinct elements. Of course, that's not very standard notation. So now you have this is an element of S16, right? 16 entities which can be permuted. They can be permuted, of course, in 16 factorial different ways. However, for example, this switching these 1 2 3s among each other, any permutation which just permutes 1 2 and 3 will just write one of these cycles before the other, right? But disjoint cycles always commute. And what is this telling you? This is telling you 1 stays fixed, 2 stays fixed, 3 stays fixed. And this is also telling you exactly the same thing. So they are the same permutation, right? So the 3 factorial permutations between these 3 1 cycles, that's going to be an overcount, because these are permutations, true, but these do not change the permutation that we are talking about. Is that okay? Okay, when I say permutations, I mean these are permutations of the 16 objects, that's correct. But if I do that to this cycle structure, I'm not getting a new permutation, I'm getting the same permutation. Well, what factor do you get from 4 5 and 6 7? and 8, 9. These are 3 2 cycles. What do you get from there?
3 factorial into 2 cube.
You get 3 factorial from the fact that you can permute them around, but even within each cycle, 4 5 and 5 4 are entirely the same thing, right? So you get a factor of 2 from this, factor of 2 from this, factor of 2 from this. That's a 2 cube. Here you have only 1 3 cycle, right? But you have a factor of 3 from there, because 10, 11, 12 can be permuted around cyclically. 11. So basically, it doesn't matter which one you start, which one of the 3 elements you start from. You write it as 10, 11, 12, 11, 12, 10, or 12, 10, 11, you get the same cycle. So for any k cycle, there are k ways of writing them without changing the cycle. Similarly, this one gives you a factor of 4, because 13, 14, 15, 16 start at any number, you can write the cycle again. So in general, the formula is and so on. So that's the number of elements in a given class, the general formula. So let's just use that here. 1 cube, that's straightforward. What is this going to be? Number of elements here. Let me just write down in red. Come on. 1 cube means 3 1 cycles. So use the formula. N factorial is how much? 6. 3 factorial, right? Divided by? Yeah.
1 cube.
1 cube and that's 1
1 factor.
Right? What factorial?
3 factorial.
Yeah, so this is going to be 1.
Yeah.
And that's trivial, right? 1 cube is 1 stays 1, 2 stays 2, 3 stays 3, the identity. And in every group, the identity always stays in its own class by itself. So that has to be 1. So what is this? How many elements here?
3 factorial by 2.
So the answer is
3.
3. And what about this one?
3.
No, that can't be 3, by the way. That would mean that you will end up with 7 elements for the entire group. The group only has 6. You can easily figure out it has to be 2.
2.
Because 4 are gone. But it's 2 simply because you are taking 6 factorial, dividing it by what? Oh, sorry, 3 factorial and dividing it by what?
3.
There's only 1 3 cycle, right? So you're just dividing it by 3. The whole thing is 1 2 3, 3 2 1. Sorry, 1 2 3 3 1 2 and 2 3 1. They're different permutations, but they're the same cycle. Whereas 3 2 1, so in this case it's just cyclic and anticyclic, right? There are only 2 possibilities. So this is the class structure. By the way, we have talked about S3 often in this class because we have talked of S3 as being isomorphic to the symmetry group of the equilateral triangle, right?
Yes, sir.
And if you look at the isometry, you can figure out what they are simply from the class numbers. This, of course, is the identity operation. This the 3 elements in the same class, these are the 3 reflections. Okay. And it's easy to see what is this here. 2 1 means a typical cycle will be something like this. Keep 3 unchanged, flip 1 and 2. But that's exactly what happens to the vertices of the triangle, remember? 2 vertices get swapped, 1 stays put when you reflect along a median. So this is just akin, these are what the 3 reflections map onto. And this one, the 3 essentially 1 2 3, something like that. It essentially flips all of them, right? When you do a 1 2 3, you actually moving each and every one of the vertices. That's actually rotation. There are 2 rotations, and these 2 rotations correspond to these 2 things. So that's a connection between the triangle and this one. Right now, what we are looking at is how to build up the character table for this. And Here also we have the advantage that for Sn we already know 2 character tables for free, 2 characters for free. For every group we know this. But because we are talking about the symmetric group, we actually know the alternating representation as well, which means this one is a 1. Of course, that's trivial. The identity is always a 1. And where do you put the minus ones? Remember, odd permutations become minus 1, even permutations become plus 1. That's the character. So which one are the odd permutations here? Yes?
It's the second class.
Is?
2-1. 2-1 class.
This is what? Minus 1.
Yes, sir.
Yeah, this is minus 1, this is plus 1. I hope everybody understands that. This involves one transposition. That means one switch, that's what an odd transposition is, right? Odd permutation is odd number of transpositions. Okay, so 2 come in for free. The third one, we already know the answer for the third one. But let me just try to show you how you would use our result to figure that out. Okay, remember for S3, what we are actually using here is a subgroup. So which of these is a subgroup of S3? The previous ones, which one is a subgroup?
So, could you repeat the question?
So S3 is our group G, for which we are trying to build up the character table. We have found out 2 of the characters without any work because they all Sns have those 2 characters. But we want to find out the third one. Or we don't even know whether it's the last one. There could be more. Could there be, by the way? Could there be more?
No.
No, because we know the number of classes, right? We know that there are 3 classes. There can be only 3 irreps. So the third one is what I want to find out. Of course, at this stage, I don't need to use Frobenius' formula because I have orthogonality and so on. I can easily figure out the last line. But let's just say we use none of that. We just use Frobenius. That is, we just use the formula we worked out a while ago. But for that, we need a subgroup. Okay? So the whole idea behind Frobenius' method is what can a subgroup tell you about the characters of a group? So I have this group S3, but do I have a subgroup of it on display somewhere?
The rotations and the identity.
Yeah, but there you're thinking in terms of the triangle, right? Think in terms of Sn, permutations.
All permutations, even permutations.
Really?
I mean,
True,
if we
but,
multiply any even permutation, we get an even permutation.
True, perfect. That's actually correct. But however, you don't even need to worry about even and odd. It's even easier than that. Any group of permutations of smaller than 3 objects would be a subgroup of S3, right? In this case, what you are saying is correct, and that's the one which we are looking at. But frankly, in general, for Sn minus 1 will be a subgroup, right?
Yes, sir.
You just hold the nth element fixed, and that's it. So for S3, S2 is a subgroup, right? That's why I was saying it's already written here. S2 here will be our H, S3 will be our G. Of course, that means that these will be our phi1 and phi2. And we are going to try to find out a compound character for capital G using whatever theory we have learned. Okay? Last আছে একটু পরে করি। Is that okay with everybody?
Yes, sir.
Of course, it might be that you might think that we are overdoing this because this is a dead horse. We have already done this before. But I'm just going to try to illustrate our technique right now. And then we are going to do it for S4 quickly so that you can see whether that is really useful. Because S4 is very difficult to do otherwise. So the third one is what you're aiming at. But for this, what we are going to do is we want a compound character to begin with. So what one can you find out? One easy way is just use this. Forget about the full formula. I need one compound character. Let's just use this. This is something you will always get, which is simply this. This is a compound character, not necessarily one which belongs to the irreducible table. So chi3 will be somewhere here. What I'm going to do, remember, is our formula that we had is this is where you use the identity representation. This one. Okay, so for this, what you have to identify is well, these are the three classes: C1, C2, C3. Which of them have overlaps with S2? Which of them don't? So remember, S2 is a permutation of two objects. These are permutations of three objects. So of course, when you're talking about permutations of three objects, and then you say, okay, let's look at the subgroup with permutations of only two objects, you're saying let's hold one of the objects fixed. Okay. So which of these classes have an overlap with the classes of S2? Which of these don't? So this one, for example.
The first two classes of S3 have overlap with S2.
Right. Why doesn't the last one have an overlap with S2?
Because no element is fixed in the in a three side.
Right. In the last one, every one of the elements moves, so there is no one cycle. Right. The point is, for S2 to be for an element of S3 to be an element in S, to also be an element of S2, there has to be at least one cycle. Right. There is one element which will not move. This one has no one cycle, so this one is out. So for this, of course, it's not really out. I can find out what is psi is. Let me move this stuff away a bit. Take us some space. For this one, you'll have 0. For this one, what will you have? Well, mod G is 6. Mod H is 2. Right? You get 3 times what fraction of the elements here are in the subgroup. Of course, this is the identity. It's in the subgroup as well. So 3 times 1. Right? Clear? Is it okay? You're just using this.
Sir, could you repeat it again? 3.
I'm just using this. I'm for this particular class. This is C1, right? See, what does C1 break into in terms of in terms of classes of capital H? It doesn't break at all, right? Identity is a single class, no matter whether it's in the group or in the subgroup. So you get 6 by 2, just the order of the two groups dividing each other, times nkj, which is 1. How many elements in Cj actually belongs to kj? All of them, 1 by 1. So that's what you get. What do you get here? This takes a bit of thought. This is 3 again, that's a 6 by 2, that's the same, right? But nkj and cj. Now let's look at T1. Here is small enough so that you can write down all of the things. This is a 2 cycle and a 1 cycle. So you have 1, 2, 3. That's one element. There are 3 elements, right? 1, 2, 3 is one of them. 2, 3, 1 is another. 3, 1, 2 is another, right? But let's say when we fix our subgroup, let's say we are going to say take the subgroup of S3 where the third element is fixed. So all 3 of these are not in S2, right? Not in my S2. Is that correct? When I identify S2 as that subgroup of S3 where the third element is fixed, all of these 3 elements which make up this class, they are not in S2, right? Which one is?
First one.
Only the first one. The other 2 are not. So nkj by ncj. How much is that? What's this ratio?
1.
1. No, not 1. NKG is 1. There's only one of the three elements in CJ which is in our class KJ. Which is
1
in
by
E.
3.
It's 1 by 3. So ultimately the final result is really very simple. After this lot of rather complicated group theory, the result is trivial almost. You see 310 is a compound character for my group S3. That's all we have. Okay. Doesn't sound like much, but first of all, is this a compound character? Well, compound character terminology works both for simple and compound. That is, compound character is just a generic name. It means it refers to all characters. When you say a character is simple, you say that you are saying that it corresponds to an irrep. So first of all, is this character also simple? How would you check? You know it's not, by the way, because you happen to know the character table of S3, but let's say you didn't. Then how would you check whether this is a simple character or not?
Sum of squares over all classes and see if it's a multiple of the size of the
Sum of squares over all elements, actually.
Yes, sir.
So when you are doing it for all classes, what you should do is 3 square plus 3 times 1 square. All elements, that's why every element of the class contributes the same amount. So 9 plus 3, that's 12. So what's your conclusion?
It's not an irrep.
It's not an irrep. It's not a simple character. So the character is not a simple character because it's not 6. It's only 2 times 6. Of course, that's a good thing because it has to be some integer multiple of 6, right? But this 2 is really sum of the squares of the number of times different irreps occur in it. So how many times do irreps occur in it? How many irreps occur in it? This is simply sigma m alpha square, right? Of course, I'm not talking of the normalized chi vector here. I'm just talking of this vector chi, if you have written down. So what does it tell you about the m alpha? It's sum of m alpha squares is 2. So what does it tell you about the m alpha? Squares of integers adding to 2.
1 and 1.
1 and 1, right? So that immediately tells you that this has to have 2 simple characters embedded in it. And one good thing is, then we could have been out of luck, by the way. It could have been that those 2 are just these 2, right? Once each. Could have been, right? But that, of course, would have been a disaster because that would have not given us any new information, number 1. But number 2, thankfully, we know it's not possible because if you had these 2 ones, then the character table would have been 202, which is, of course, not 310. So we know already that this has to have at least one character which is not in this list.
Sir, but it could be possible in some other situation, right? How are we sure that this compound character will have some unfound character?
Of course, we are not, but we don't have to stop here, right? Because remember, we just use a simple thing we just use this representation. We also have this representation to play with. Okay. We know all the irreps of the subgroup. So the irreps of the subgroup doesn't have only one character line. This one is particularly simple. So we focus on that. And that will be quite useful for many purposes, but that's not the only one we have. Remember, our formula is not this. Our full formula is this. Where you take the mod G by mod H ratio, you take the number of elements in the ith class within Cj of H, divided by number of elements in Cj, then you multiply it by the corresponding character for that class. That's the full formula. The particular formula we used was because we use phi mu's are all 1. Is that okay?
Yes,
so
sir.
we have more to play with. It's not just that. If that had been the only formula, then your concern would have been right. What is to guarantee that this will give you a new result? Of course, it will not can't give you many new results, right? Because for larger, here of course I have only one more line of the character table to write down because I have only one more class and one more irrep. In general, that may not be correct. In general, you will need to write down several lines. But quickly, let me just finish this. 310. I know it has two irreps building into it, but which ones? I can easily figure out one of them. Just find out how many times chi1 occurs into this. We know how to do that, right? Is it okay? Yes or no?
Yes, sir.
And how do you find that out? Well, just find it out. It's 3 times 1 plus 1 times 1 times 3 plus 1 times 0 times 2. That's 6 divided by 6. So this occurs once. Okay. In fact, this occurs 0 times. 3 times 1 plus minus 1 times 1 times 3 plus 1 times 0 times 2 by 6. Of course, we already knew that. Both of them couldn't possibly occur. But now we know this one occurs once. And we have that is enough information to figure out the other one. Can you tell me what that is?
20 minus 1.
It is going to be 20 minus 1. Of course, you know the result, but so it's good to see that it's emerging. All you do is just take this 310, which is a compound character. You know it has 111 in it. Subtract. You've got 20 minus 1. That has to be a compound character, right? But is it also a simple character?
We can just check again by using.
You can just check using the irreducibility criterion. 2 square times 1, that's 4. 0 square times 3, that's 0. And minus 1 square times 2, that's 2. So it's 4 plus 2, 6. By 6 is 1. Irreducible. So you've got a simple character. Done. So our character table is built up. Okay. So although building up the formula took quite a long time, using it doesn't take much long. Right? Okay, but it might seem like a trivial thing, but after all, too much hard work for very little final bang for whatever buck you have put in, because all we have managed to do is find out S3, and we already knew S3. So let me quickly show you how to do S4. For that, you will need S3 as a subgroup. So 1 cube, 2, 1, 3. Number of elements, we wrote them down, 1, 3, and 2. And we have these 3 irreps, which are now my phi 1, phi 2, phi 3. They were chi's for S3, but when you are looking at S4, these are really the characters for the subgroup. So this is the table I had for S3. What about S4? First, conjugacy classes, 1, 4. Right? So I've got all possible. How do you find out conjugacy classes? Just figure out how many ways you can break up the number 4 into non-negative integers. Non-negative because when I'm saying 3, 1, I really mean 3, 1, 0, 0. That is 3, 1 cycles. 1, 2, sorry. 1, 3 cycle, 1, 1 cycle. No 2 cycles, no 3 cycles. So again, the sizes. This is 1. This is 4 factorial by 3 factorial times 1 factorial. Right? Really? What will this be? How many here?
4 factorial by 3.
4 factorial by 3. That's 24 by 3. That's 8 elements here. This will be
4 factorial by 2.
so this is a 2 square, 2 cycles. Right, that's the way to write it. So this 4 factorial by 2 factorial for the into 2. 4 factorial by 2 for the same reason you had a 3 here. Permutations within a cycle. And the 2 factorial is for permutation of the cycles themselves.
2 factorial into 2 square.
2 square or 2?
Each 2 cycle can be transposed.
Exactly. So 2 square. Right. 4 factorial by 8. That's 3. How many here? This is 4 factorial by 2 and a 2 factorial because of the 1 square. Right? That's 6. And this is 4 factorial by
4.
4. That's again 6. So let's check whether this counts. 12 plus 12, 24. Done. Okay. So these are the 5 classes you have. You will have 5 irreps to build up, and you have only 3 irreps for the previous line. So now notice that the number of irreps are growing faster than 1 each time. So you need to work a bit harder, but not very hard. Okay, the questions. First of all, you can immediately write down 2 representations here trivially. What about the alternating one? This is 1. 3, 1 is going to be?
-1.
3 is a 3 cycle. 3 cycle is even or odd. There's something you learned long time ago, right? Even before you learn our formula or permutations. Cyclic order, is that an even permutation or odd permutation? 1, 2, 3, 2, 3, 1, 3, 1, 2. Even or odd? How many transpositions?
Even.
This is even. What about this? 2 square. 2 square is something like 1, 2. One element would be something like this. There are, of course, 3 elements. One of them would be 1, 2, 3, 4. Is this an even permutation or an odd permutation?
Even.
Even. What about this one?
Odd.
This one? The 4th cycle, 1, 2, 3, 4. Okay.
Odd.
That is 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. Is that even or odd? How many switches can you have to do this? 1, 2, 3, 4. 4. 1 goes to 2, 2 goes to 3. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. How many switches? You can start with 1, 2, 3, 4. Then make 1 and 2 jump across. 2, 1, 3, 4. Then make 1 and 3 jump across. So get 2, 3, 1, 4. You can finally make 1 and 4 jump across to get 2, 3, 4, 1, which is what you want finally. So how many switches?
5.
How many switches? 5. You can do it in 5. The minimum is 3, right? Just 3. One. I wrote that 1, 2, 1, 3, 1, 4.
Where
Just
is it?
make the 1 jump across each one of them. And this is something, by the way, this is the kind of thing which you have to be able to do in 0 seconds flat if you want to do things like, say, fermionic operators, how to handle them. You can't spend so much time thinking about them. This is odd. This is the -1.
Sir,
Yeah.
I did not understand. I mean, we could have a odd cycle even in 3 cycles, right? I mean, I didn't understand why
No.
one.
The question is this cycle 1, 2, 3, 1, 4, right? So basically, just look at this one and ask: Is this an even permutation or an odd permutation? Just look at the basic one.
Okay, so
And apply that. Give the number to everything in the cycle. That's
okay,
how the already representation goes. I'm not saying whether every element in that cycle is a even cycle or odd cycle.
okay.
Now, two of the character lines gone. What about the further ones? So for this, we want to figure out our compound characters. So let's take a compound chi, which I'm going to form just using the mod g by mod h times the fraction of numbers formula. Easy one is this one, right? Because the identity of, remember what we are going to do is take the last element as fixed, keep 4 fixed. Okay. And then ask how many elements, So for example, this one definitely does not have overlap with the group capital H, right? This one moves every one of them, right? What about this one? Two square, two cycles, right?
Even it should be disjoint.
Definitely doesn't have a one cycle in it. So these two which don't have one cycles in it must be 0. Okay, this one and this one. But the ones which do have one cycles in them, among them, certain elements are going to be in the subgroup. Not all of them, but the one in which the one cycle involves the letter 4, that's going to be in the subgroup. The 4 is arbitrary. You could have chosen 3 or 2. You just get isomorphic subgroups. I'm just choosing one of them. The 4. So this one, this is only one element. Of course, here is pretty simple. S4 is 24 in size. S3 is 6 in size. So there's a factor of 4 which you get. And you have to multiply by this the number of elements here which are also in the subgroup. How much is that?
1.
1. So there's a 4 here. That's easy. For this, you have a 4 from the ratio of the sizes times what? Question is, how many of these 8 are in the subgroup? Oops.
Three.
Which, by the way, which class up here belongs to this class? This class, which elements of S3 actually belong to this class?
Third class.
This one, right? And do both of them belong to this class?
Yes, sir.
Both of them do, right? So that's actually 2 out of 8. So that's a 1. So finally, 2 1 square. The typical element here would be something like 1, 2, 3, 4. There are 6 such elements. Okay. How many of them belong to that class?
3.
All 3 of them. You're sure?
Yes, sir.
Okay, good. So that will give you 4 into 3 by 6, right? That gives you 41020 as your compound character. So first of all, let's check. Is this reducible or irreducible? Of course, we could have gone through the representation theory by saying that there are 5 classes, so 5 irreps, whose sum squares of sizes should add up to 20 or add up to 24, and so on. But that doesn't rule out a 4-dimensional irrep, right? You can still have a 4-dimensional irrep there. So the standard way that we have been using so far, actually that will really be rather difficult to use here. Even the dimensionalities are not so easy to get. 5 squares which add up to 24. That's not that easy to figure out. But here, first of all, we have got a character. Let's check whether this is an irreducible character or not. For that, what you need to do is 4 square plus 1 square into 8 plus 2 square into 6. So 16 plus 8, 24 plus 24. 48. Of course, I hope the calculation is straightforward to everybody. And then you divide by 24 and you get 2. So what does this tell you? Firstly, it tells you it's not irreducible. Secondly, it tells you that it can have only two irreps in it. And let's check. Does it have any of these irreps in it? So does it have this one? In fact, this one is pretty easy because remember you have positive numbers here, 4, 1, 2, right? There's no chance that the dot product of this with this vector, which has only ones, will give you 0. So that better be in it. Let's check. 4 times 1, 4 plus 8 plus 2 times 6. Right? That's 24. Divide by 24, you've got 1. So this occurs once. So one irrep I can immediately write down. 3, 0, minus 1, 1, minus 1. That's our third irrep. Is that clear?
Yes, sir.
Okay, that's not, of course, done. We are not done here because we have got only 3 irreps. We need 5. So what would you do? Well, you have 2 more representations to play with. This one and this one. 2 more representations of subgroup to play with. Use that. There are 2 more compound characters. And then once you've got the 2 more compound characters, try to see whether they are compound or simple. They will turn out to be compound. Try to see whether the 3 irreps that you have already found out are in there. If they are, subtract them out. Check whether whatever you have got is simple or compound. If not, do it again. If yes, you're done. You see that? Now, what could be a problem with this thing? There are 3 irreps already. You already have 3 irreps for the subgroup. So you get enough lines. So what's your problem? What can be a problem?
The compound representations might have already known irrep.
So one possibility is it might not give you something new. Okay, that's one possibility. It might give you one of chi1, chi2, chi3 already again. Or maybe just chi2 plus chi3. It will be compound, but it will not be a irreducible representation. Okay, there's a bit of theory which shows you that that will not happen, but that's a bit of involved theory. I'm not going to go into that.
So
yeah.
does it mean every compound irrep that representation we find will have some not found irrep?
Yes, that's actually true. But the proof of that is a bit difficult, so I'm skipping that. Already we have done quite a lot of nasty calculations here. The calculations are straightforward. It's just that, but another possibility could occur. Will not occur for this. So this is the homework. Complete the other 2 lines. But will not occur for this, but could have occurred. Let's say you find 2 more compound characters using these 2 lines. Okay, let's say you do that. When you do that, you have to be a bit careful because it's possible. Will not happen here once again, but it's possible that those 2 could be, say, something like this. May not have any of these. Chi1, chi2, chi3. Right? Is that okay?
Then how do we do that if we face?
But then you have 2 compound characters. You can always write them as chi4 plus chi5. Okay, bad notation because here this sort of implies that chi4 and chi5 are irreps. But let's just forget about the irrep business right now. You have 2 compound characters, you can always write them like this, let's say. And from that, read off chi4 and chi5. New compound characters. And all in such cases, you will find ultimately that you are going to get an irrep out of this.
So, but I mean, whatever the compound representation we get, it could be some combination of chi4 or chi5, like 1 and 2.
No, all I'm saying is it will be some combination of chi4 and chi5. It doesn't have to be some odd difference. You're right. All I'm saying is that would be if you insist on chi4 and chi5 being irreducible. Okay. All I'm saying is if you have 2 compound characters, you combine them together, just add or subtract them, you are going to get new compound characters. Okay. In fact, by the way, from the irreducibility criterion, you can figure out exactly how many times characters go in. Say for example, let me just say, for the sake of definiteness, let's say I find a compound character using the second line, and I find, in fact, I will find in this case that it will have exactly 2 irreps in it, once each, because you've got sigma m alpha square equals 2. That's really the ratio, right, of chi dot chi by mod g. So I know it has to be a sum of 2 irreps. If it's a sum of 2 irreps, right? If that is all you have, if it's a sum of 2 irreps, and it's not one of chi 1, chi 2, chi 3, it has to be chi 4 plus chi 5. So use that argument. Actually, that will not be something you will need for S3, for S4. For S4, you will find that the 2 will come out to be just standard compound characters which actually have something of chi 1, chi 2, chi 3 in them. Just find out which one is there, subtract, you will get another irrep which is actually a simple, another character, another line in the character table. Okay. But what will happen if you try doing the same thing for S5? So that's what I'm inviting you to do. Do it for S4, do it for S5. Complete the S4, do it for S5. For S5, you will find that S5 has actually 7 partitions. 5 has 7 partitions. 5, 4 plus 1, then 3 plus 2, 2 plus 2, and so on. S5 has 7 partitions, 7 irreps, and you will find chi 1, chi 2, chi 3, chi 4 will follow simply using this. But chi 5, chi 6, chi 7, you will find that when you try finding the next 3 compound characters, you will find that they turn out to not have chi 1, chi 2, chi 3, chi 4 in them, but they all have 2 irreps in them. So they must be chi 5 plus chi 6, chi 6 plus chi 7, chi 5 plus chi 7. So from there again you can find out chi 5, chi 6, chi 7. This procedure can be extended throughout, but it becomes more and more complicated as you go along. Okay, so this is not Frobenius's final result. This is just an illustration of Frobenius's formula and how you can use it, at least for small n's, to find out these character tables. But this works only for small n, does not really work very well for large n's. But I'm going to just indicate how to do that. Okay, not today because it's gone too long. But let me just point out one thing. Suppose you have an Sn, which means permutation of n objects, and you have some permutation lambda, some partition lambda of n, which means lambda is set of non-negative integers which add up to n. Then what you can do is you can always think of S, say lambda is lambda 1, lambda 2, and so on, with the restriction that their sum of lambda I is n and lambda 1 is greater than or equal to lambda 2 and so on. This is a non-increasing sequence. That's simply to sort of stop overcounting. Then it's easy to see that this object, this is a group, right? It's a direct product group. But what direct product is this? Suppose, so 7, let's take the number 7, n equals 7, and let's say one possible permutation is 4 plus 2 plus 1. And so we are talking of S4 cross S2 cross S1. Can you see that this is definitely a subgroup of S7? What's an element of S7? Any permutation of 7 objects, right? What's an element of this? It's a permutation where the first 4 objects of the 7 permute among themselves, next 2 among themselves, and the last one stays alone. Is it okay? Remember, in a direct product, each subgroup does its own, each group in the direct product does its own thing. So S4 would be 4 objects permuted. Let's say the first 4 of the 7. S2 will be the next 2 permuted, and S1 will be the last one. Of course, last one permuted means last one staying where it is. So if you just take the direct product of these three groups, you will only get some subset of the entire S7, because after all, and permutation which permutes, say, the fourth element here with the sixth element here does not occur in this direct product. So it's a subgroup, but each partition gives rise to a subgroup. And using the fact that each subgroup is a symmetry group, so you know everything about its class structure, because we have already figured out how to figure out all possible classes for a subgroup, and also how many elements the classes have. Frobenius used this and just some nifty combinatorics to find out a general expression to how to find out the character table for Sn. So I'm going to indicate how that works in the next class. The basic formula that he used is the formula that I wrote down a while ago. Basically, this one. So this Frobenius formula is the be all and end all of this. You use this to derive every result. But then, basically, connection between this and the kind of drawings that we had drawn, say 4 boxes, then 2 boxes, then 1 box. Permute these 4 boxes among themselves, these among themselves, these among themselves. The Young diagram plays a big role in keeping count of how many times everything occurs, and that's where the connection between Young tableaus and SN's irreps come in. So that will be for the next day. Okay, so today is Thursday, right? It is. Yeah, people are so stunned that they have even forgotten what day it is. Okay, your talks are going to start when? Who is going to start and when are you going to start? Monica, when are you going to start?
So if it's possible, can I have my presentation whenever after 19th?
Yeah, it's possible, but then everybody will have to have presentations there.
If it's okay with everyone, because I have a net exam on 19th.
No, that's fine. 19th is anyway 1 week from now, so that's. So next week I'm going to talk. The week after that, I will talk about league groups, but you'll have extra class. We'll have to find out extra times when you'll give presentations. Next class, I will just barely indicate Frobenius' method. I will not go into the details because I will just give you some of the results. The results are easy to state. And then I'm going to talk about Lie groups and Lie algebra. Then I will need 5 or 6 classes to talk about that. So till the end of the month, I will be taking 2 classes a week, but you will have to find 1 more extra slot when we can have these presentations.
So the classes will be regular and
at Tuesday, Thursday. We will keep this slot. If some other slot is suitable, we can switch to that. But basically, Tuesday, Thursdays will be as before.
Yeah, so regular classes will be happening, and we'll have to find another slot for the presentation once a week.
That could be in the evening or whenever you feel like it. Doesn't have to be in the morning or during office hours or whatever. So that's your next task as well. Okay, the home task I have given is a home task. You have to submit it. Okay, the complete S4 and S5 character tables using this technique.
When should we submit, sir?
Next week.
Sir?
Next week, anytime next week. Before your net exam, but shouldn't take too long. Or, okay, maybe after.
No, sir, I was just talking about the presentation. The homework can be done.
The presentation would be the week after, starts the week after that. So the week starting on 22nd till the end of the month. We can, of course, continue into the beginning of December as well a bit, if that's convenient. That is your presentations. So we will have 2 weeks in the end of November. We can have the first week of December as well.
So, but there are six people in the course.
Yeah. So if you have 3 weeks, 2 slots a week, maybe a 2-hour slot. The 2 people presenting. Let us live through that. So 2 presentations in a week in 3 weeks. Otherwise, we'll have to start next week. That may be too early. I have to give you grades, so it can't be too late. Okay, let me just stop recording this.